Okay, so one final example to run through of this sort of rearrangement. The only difference here is instead of our angle being x, we have changed our angle to 2x. But that is matched by having a 2x over here. And what I hope you will see from this example is that that 2x really doesn't impact our question all that much. Nothing greatly changes. So we're going to start in the same way. We're going to write out what k sine 2x plus alpha expands to using that identity from our formula booklet. And then we're going to do some comparing and find our missing values. So identity in the formula booklet says that that should be sine of 2x cos of alpha plus, matching the pluses for because it's a sine one. And then we've got cos of 2x sine of alpha. Expand that out, we get k cos alpha, and like we did last time, just swapping our terms over. And again, k, and this time sine alpha, cos 2x. Now we're in a good position, exactly where we were before, because we have a cos 2x and a cos 2x, which means that the bit that comes before our cos 2x matches with our bit that comes before our cos 2x up there. So we get k sine alpha is equal to 12. From that first comparison, our second comparison is that sine 2x matches sine 2x up here. And so the thing in front of the sine 2x matches the thing in front of the sine 2x up here. So we get k cos alpha is equal to the thing in front up here, which is 5. Now, this is all looking very familiar, and so we can proceed as we have with every other example by doing k sine of alpha all squared plus k cos of alpha all squared. And what is that? Well, that is 12 squared add 5 squared. This whole section here, using that same approach we do each time, simplifies to k squared. As I say, I'm not writing all that working. You can reconvince yourself every time if you want to, but I wouldn't bother. 12 squared add 5 squared, even on the calculator, you can just pop that in. You get 169. And so k equals 13. We're keeping the positive square root because we want k greater than 0. Same thing, finding alpha. We want to do our division method to get that. Sine over cos gives us 12 over 5. This side, as with each example we've done so far, simplifies to tan alpha. Quick cast diagram. And we're nice because we've got no negatives here. So really we could be in that section or that section for tan being positive, and both sine and cos are positive as well. So we're up in this quadrant here. So we're just looking for a relative acute angle, which is tan to the minus 1 of 12 over 5. Now, one thing I haven't mentioned so far, if this was in radians in the original question, all you'd want to be doing here is just working this out in radians. We're in degrees for these questions, but that is the only alteration being in radians would make to our method. Putting that in the calculator and rounding it, we get 67.38 degrees. So our final conclusion, putting together all the bits that we've just done, 12 cos 2x plus 5 sine 2x equals, and from what we've just done, k is 13. So we've got 13 sine, and I'm just following this form here. So I'm putting my k in sine. We keep the 2x there because that was in our original form, and our alpha, which is 67.38. And we're finished. We've completed what we were trying to show. So once you get familiar with these steps, not too many dissimilarities, even as I very slightly vary the question, the method remains extremely similar all the way through. So have a go at the questions now. You've seen lots of examples. You'll find that task 2 is a small extension to this skill. And so hopefully when you get to task 2, you'll see why I've put effort into this part, and the second part, the task 2, becomes much easier once you've mastered this and you've seen this a few times. So have a go at task 2, and then we will run from there with task 3, which is a slightly different take on all of this. Okay, so task 3 is a bit different, whereas task 2 is very much building on this skill.